Just under 1,500 years ago, something terrifying happened to the world's climate. Something nobody could understand. The sun began to go dark. Rain the color of blood poured from the skies. Clouds of fine dust enveloped the earth. Winter gripped the land for 2 years. Then came drought, famine, plague, death. Whole cities were wiped out, civilizations crumbled, and nobody knew what had happened. It was a catastrophe that affected millions and millions of people all round the world. But what was it?
The mid-6th century catastrophe was the most important date in the history of the past 2,000 years. It really did lay the foundations of the world we live in today.
For 5 years, in the attic of his unassuming suburban home, David Keys, a writer on history and archaeology, has immersed himself in a worldwide investigation. He's consulted over 80 experts on drought, famine, floods, cosmic and ecological disasters, epidemics and ancient wars. He's scoured the annals and chronicles of the 6th and 7th centuries AD from all over the world. His book tells the story of a catastrophic climatic event buried in the heart of the Dark Ages, which Keys believes totally altered the course of history. The mystery, which has so tantalized him, began at a conference on archaeology in 1994.
One particular talk really amazed me. It was a lecture given by a dendrochronologist, an expert in tree rings, called Mike Bailey, and he was giving a lecture about how all the tree rings in the world really went haywire somewhere in the middle of the 6th century.
"30 years ago, when he was a physics student, Professor Mike Bailey of Queen's University in Belfast pioneered a revolutionary idea in a totally different field to his own. He devised a computer system which would put trees to scientific use. He had realized that trees had the potential to become the silent witnesses of the world's changing weather, going back thousands of years. Every year, trees put on a new layer of growth within the bark. These layers show up as rings. Every ring varies in width. A wide ring is a year of good weather, a narrow ring a bad year. The pattern of wide and narrow rings is distinctive. Each ring sequence can be matched with the rings of previously felled trees and precisely dated. The computer program which matches the patterns of the rings was Mike Bailey's invention, and it's now used by laboratories all over the world.
Over the last 30 years in Northern Europe, a variety of people, a variety of laboratories have set out and worked back from known felling dates taking you back through long ring records of living trees and then overlapping to patterns from historic buildings, for example, fitting together these sort of long ring patterns, going back hundreds and eventually thousands of years.
It's by painstakingly analysing and overlapping the patterns of older and older trees that a complete, unbroken record of tree ring widths is built up.
So you've got this sample with its very clear character change just here. When we processed another sample from the same building, we could see that it came originally from the same parent tree, and you could extend the pattern back from the first sample right back through to the beginning of this sample.
Many samples have to be analysed by Mike Bailey's computer program to get the average width for every year. It took 14 years to build up the complete data just for Irish oaks. This tree record is now telling Irish scientists what the weather was like every single year for the last 7,500 years.
If you think about that, that's an astonishing position to be in. We can interrogate for any calendar year in the last thousands of years what trees thought of their growth conditions over a big geographical area. That information simply didn't exist before. But what we're interested in is, why did this tree go narrow at this point and narrow again at this point? What is the environmental information which is actually stored in the patterns?
David Keys went to Ireland to see for himself the mysterious 6th century event stored in Mike Bailey's tree rings.
Yeah, shuffle through here, David.
It was 10 years ago that Mike Bailey noticed his oak rings went abnormally narrow in the mid-6th century AD. Signs that something very powerful was stopping the trees growing.
539, 540, 41, 42, extremely narrow.
Bailey then told Keys of similar evidence from Europe, particularly from a colleague in Finland.
He sees a really abrupt drop in 536, a bit of a recovery in 537 and 38, and then it drops dramatically into 542. So you're beginning to see a pattern.
And that pattern wasn't just confined to Ireland and Finland. By contacting other labs, David Keys found that wherever you looked in the world, in the mid-6th century, trees were having a terrible time. Foxtail pine rings from the Sierra Nevada mountains in California showed that 535, 536, and 541 were 3 of the 4 worst years in the past 2 millennia. In Chile, Fitzroy trees record the greatest summer growth drop of the past 1,600 years. In Siberia, a 20-year decline in tree growth in the 530s and 540s was the most serious in the past 1,900 years. So why were the trees not growing? Was it dark, cold, natural pollution, or drought? For Mike Bailey, the answer lay in a microscopic examination of a 536 AD oak ring. Cells normally seen in winter were showing up in summer too.
A colleague in Germany sent me this photograph of one of his German oaks. The tree puts on a line of these large spring vessels, and it then puts on fine cell wood during the summer and goes dormant, and then it does again the next year. So each year's growth is from the beginning of one line of vessels to the beginning of the next. And in this year, the year 536, the vessels are enormously small, and they're also distributed right through the summer. So it's widely reckoned that this phenomenon is due to frost damage.
The implication from this kind of worldwide evidence was that the weather was extremely cold for long periods in the mid-6th century. Mike Bailey also had archaeological evidence from Ireland which backs this up. Much of the wood that he dated came from crannogs, wooden island forts that people built as refuges in times of trouble and clan warfare. Bailey took Keys to the remains of one in Loch Catherine, near Omagh, to look at the submerged timbers that once formed the outer wall.
My first inkling that there was something going on came from timbers, specifically from sites like this.
The mid-6th century marks the beginning of the construction of crannogs. Bailey believes that this was due to the hostile conditions stemming from the climatic disaster.
When you look at the overall picture, there seems to be about a decade of really bad conditions, starting in 536 and running on to the mid-540s at least. The implication from lots of bits of evidence is that it was extremely cold, and that this reduced sunlight and cold caused crop failures. So basically, people in an area like this would be forced back onto non-agricultural produce. They would be forced to fish, they would be forced to hunt, and that would put a lot of strain on a population which was used to having agricultural produce to see them through the winters, for example. So I think things would have been fairly bleak here.
Keys was now hooked, not just by the tree ring evidence that it was cold, but also by the fact that people seemed to be suffering too. His next step was to see whether there were any written accounts from the time of the climate falling apart. By far the greatest civilization of the 6th century was the Roman Empire. Rome had been sacked 100 years earlier by Huns and Goths, but now the empire was resurgent with a new capital in Constantinople. Once again, it was the center of Mediterranean culture. By contacting classical scholars, Keys unearthed many highly significant Roman accounts of bizarre weather. One eyewitness, a Syrian bishop, John of Ephesus, describes the extraordinary events during the years 535 and 536 AD.
There was a sign from the sun, the like of which had never been seen or reported before. The sun became dark, and its darkness lasted for 18 months. Each day it shone for about 4 hours, and still this light was only a feeble shadow. Everyone declared that the sun would never recover its full light again.
Historians of the 6th century empire do not usually record climatic events unless they are something really stupendous. A natural event like a comet will get mentioned. Now, in the 530s, the fact that John mentions a 2-year dimming of the sun indicates that it was significant. John, writing in Constantinople, mentions it. Cassiodorus, writing in Italy, he too refers to a dimming of the sun.
We have had a spring without mildness and a summer without heat. The months, which should have been maturing the crops, have been chilled by north winds. Rain is denied, and the reaper fears new frosts.
These accounts from the Mediterranean and Middle East were extraordinary enough, but what about the other civilizations of that time? Keys scoured records from North and South China, Korea, and Japan.
And as it turned out, there were, out of, say, well over 30 sources, there were around a dozen which actually refer directly to the darkened sun event or to its consequences, to its immediate climatic consequences.
In 540, the Japanese great king wrote, "Food is the basis of the empire. Yellow gold and 10,000 strings of cash cannot cure hunger. What avails 1,000 boxes of pearls to him who is starving of cold. And the Nanxi ancient chronicle of southern China records, yellow dust rained down like snow. It could be scooped up in handfuls.
As the research continued, I began to realize more and more that this disaster had really enveloped the entire world, that it just wasn't just a few places, but it was virtually everywhere. The only question was, what was causing it? There seemed in my mind only three possible answers to that. Either an asteroid, or a comet, or a volcano.
Imagine living in the middle of the 6th century, suffering a climatic catastrophe, an event so horrendous that trees hardly grew for years and the sun was dimmed. Whatever it was, it would have taken thousands of cubic miles of dust to be hurled into the atmosphere to cause this permanent winter. Was an asteroid, comet strike, or volcano responsible? At Los Alamos, the birthplace of the atomic bomb, scientists have been studying all the possible atmospheric consequences of nuclear strikes and cosmic collisions.
We certainly have plenty of evidence that the Earth is struck repeatedly by asteroids large and small, comets large and small. You have to have a big thing that hits the ground in order to have a climate effect.
Extraterrestrial bodies come in all shapes and sizes. Meteors are small rocks which roam space, occasionally hitting planets, usually causing little damage. Asteroids are big meteors. When these things hit the Earth's surface, they explode, churning up vast amounts of dust and debris. David Keys asked an astrophysicist to calculate how big an impact would have been needed to generate a climatic catastrophe lasting at least a decade.
And so what we can say is that the total number of particles in the atmosphere, because this is one, then rho is around 1 over kappa L. To cause a major climatic catastrophe that would last decades, we would need an impact by a rather large asteroid, say 4 kilometers across.
It would take an even bigger comet to create the same effect. A comet consists mainly of gas and ice. This gives them their distinctive tail as they move across the sky. Because they're less dense, Alan Fitzsimmons has calculated that it would take a 6-kilometre-wide comet to affect our climate. Such a crash would have a spectacular effect on our planet.
When it was just over 2 days from impact, it would only be seen as a very faint star in the night sky. Now, as it approached us, as it got closer and closer, we'd slowly see it brighten and grow larger until about 30 minutes before impact. It would be about the brightest thing in the sky, and by then, of course, we believe everybody would have noticed it. But we wouldn't be able to do anything about it. Now, the time it takes for that asteroid to travel from the top of the Earth's atmosphere until it reaches sea level is only 8 seconds. So we'd see this brilliant fireball, all the time, of course, making no sound because it's travelling about 20 times the speed of sound. The first sound we would hear would occur minutes after we see the huge flash of light when the asteroid strikes the Earth's surface and is instantly vaporised in a ginormous fireball.
Could this disaster have happened without at least one civilization noticing and reporting it? no civilization at the time records any such event. In addition, scientists have found no evidence of a crater left by an impact from the 6th century.
I mean, that's just yesterday. In geologic time, it'd be a big crater. We'd know about it. Certainly that happened 65 million years ago when the dinosaurs died. But I don't think it happened in the 6th century.
But the lack of a crater alone does not rule out a comet or asteroid strike. 70% of the Earth is covered in water. Could it be that the impact was on the oceans?
If the asteroid landed in the ocean, then the initial wave caused by the impact would be miles high.
There would have been humongous tidal waves, big, huge tidal waves that would have swamped the coasts over the margins of whatever ocean it struck.
The tidal damage would have traveled miles inland. Again, no civilization recorded such an event. And scientists haven't detected any significant interruption to the growth of coastal plants at this period. There doesn't appear to be any evidence of an asteroid or comet strike on Earth at this time. The search seemed to be narrowing down to a volcano. But could there be another extraterrestrial explanation? This time, not a complete comet hitting the Earth, but one which had fragmented and scattered throughout the atmosphere. It's a theory Mike Bailey suggested to David Keys.
Well, the bombardment event has been, if you like, classically defined as a large number of pieces of comet arriving in a short period of time and exploding in the atmosphere. And the model for that is the 1908 Tunguska impact over Siberia, which was a single object which probably caused about a 20 megaton equivalent size of explosion.
The 1908 Tunguska event was an example of an airburst explosion. A lightweight meteor hit the Earth's atmosphere and exploded in the air. While the shockwave caused massive local destruction, there weren't enough microfine particles released to affect the weather. But Mike Bailey believes that a whole shower of cometary debris hitting in a Tunguska-style event could affect the climate.
If you have a large number of those, you're going to just put a lot of material into the atmosphere, and you're going to cause a dust veil.
Mike Bailey believes that it's possible to use mythology to support his theory. He's analysed the life and death of one of the most famous legends of all time and reached an intriguing conclusion. 6th century Britain was supposedly the time of King Arthur. All the many later legends tell that Arthur lived in the west of Britain and that as he grew old, his kingdom was reduced to a wasteland. Curiously, the legends give the date of Arthur's death as 539 or 542 AD, right in the middle of the climatic catastrophe. The legends also tell of terrible blows which rained down from the skies onto Arthur's people. Mike Bailey thinks that Arthur's death could therefore be a symbol of something that really did happen, devastation by a comet as it shattered and crashed into Earth.
Then you look at the mythology. You discover that Arthur isn't just somebody with a nice suit of shining armour and somebody sitting around a round table. The origins of the stories are in Celtic mythology, and that one of the key figures that you can trace him back to would be the Celtic god Lugh. That Lugh is a bright solar deity who curiously comes up in the west and has a long arm, which could well be the description of a comet. And Lugh also is famous for delivering these terrible blows.
Could Bailey's myths hold a grain of truth? By a process of elimination, it now seemed to come down to a clear choice: cometary bombardment or a volcano. But which? David Keys discovered that there was one hostile area of the Earth which could just hold the final clue: the polar ice caps. For the past decade, a multinational team of scientists has been extracting 1,000-meter deep columns of ice from Greenland in the north and the Antarctic in the south. In the same way trees put on a new ring of growth each season, the polar ice caps put on a fresh layer of snow. And in each layer is a record of what was in our atmosphere.
The chemistry of the old atmosphere is in there. And even the chemistry today is changing in our atmosphere. If we combine this, we can have a record which we can compare with other records from the deep sea sediments, from tree rings, from lakes. But the fantastic thing about the ice caps is that they are directly related to the atmosphere itself.
Professor Hammer's team are testing a new Greenland core from the 530s AD that has just arrived at their laboratory. If pieces of a comet or asteroid had exploded in the atmosphere, the team would expect to find traces of rare chemical elements like iridium. If there had been a massive volcanic eruption, they would expect to find an excess of sulfuric acid, the telltale signature of a volcano. The sulfates would have been hurled up into the atmosphere by the explosion and scattered by the winds. They would have then got into rain and snow to be finally stored at the poles as ice.
And what we are going to do now is take a piece of ice out around 535 after Christ. We will have to clean it a little roughly here first. We will now bring it into this setup here, where it will be cleaned in the ends and on all sides, and then it will be cut by the steel knife so that we are not touching the core. We have to remove quite a lot to be sure that we don't have any outside contamination.
The cleaned core is sliced into 5-centimeter lengths. Each length is then melted and analyzed.
They will be measured one at a time, automatically, from now on, and the results will show up on this computer as chromatograms.
So what does the ice contain? Cometary debris or volcanic sulfates?
Here I can see the sulfate peak is increasing when I go to the next sample. That must be come from sulfuric acid in the atmosphere, and that's an indication that there's been a volcanic eruption.
And as the final result shows, it wasn't just any eruption.
I'll show you here is the sulfuric acid. And actually, these huge amount of sulfate here, lasting several years and clearly higher than anything else in this part of the record, corresponds exactly to this around 535. So there's no doubt it's a major eruption.
The evidence from Greenland seemed conclusive. Lots of sulfates and no cometary debris. But for the eruption to have had worldwide consequences, more was needed.
If you want a climatic important major eruption, it must show up with a large signal in both hemispheres. That is, you must see it in Antarctic ice cores and you must see it in Greenland.
At the moment, information from the Antarctic ice core is less precise, but from their existing data, Professor Hammer's team already know that there is a volcanic signal in the Antarctic too.
We have a volcanic signal which lasts several years. We have from an Antarctic core similar evidence as in Greenland, but not as good, not as well dated, but indicating that this volcanic eruption could have taken place.
The data from both the North and South Poles is the same, a huge sulfur spike around the mid-6th century. That strongly suggests volcanic ash caused the global climate damage seen in tree rings. The idea of volcanoes causing climatic catastrophe may seem unfamiliar. But tree rings and ice cores now show that every 1,000 or so years, massive climate downturns have happened. The mid-6th century event is simply the most recent. In fact, what surprises volcanologists is how few volcanic eruptions there have been in the last 100 years.
One of the amazing things, which people sometimes forget, even scientists, is that our century is one of the most quiet centuries with respect to volcanism. If you go back in time, in 19th century, in 17th century, 18th century, there's a lot of volcanoes. They come in lumps, say 20, 30 years, a lot of them. They even overlap in the stratosphere, mixing up. And it's not speculation, but people do think that Turner's paintings with his sunsets, it was not the taste of the artist to make them so red as they were, but they were actually painted in a time when the real sunset looked like that.
We live on this planet with over 200 active volcanoes. They may have been quiet recently, but a really massive eruption can turn the climate upside down. To create a dust veil that spreads all round the world, the eruption has to happen near the equator, as only equatorial winds can spread dust over both hemispheres. But there are over 90 equatorial volcanoes. Could David Keys discover which one caused the mayhem of the 6th century? David Keys began to narrow the search for the 6th century volcano. He knew that the highest concentration by far of large tropical volcanoes lies in an arc straddling Southeast Asia, from India through Sumatra, Java, the Philippines, and Japan. First, he turned to the greatest civilization near this area, which was then producing written records: China.
I, in great excitement, started looking to see whether there was any trace of anything happening in 535. And in fact, in February 535, there's a record of a loud bang, a huge thunderous sound coming from the southwest. And with this one, there was no mention of lightning or anything. It was merely a rather sort of mysterious entry in which they only referred to the sort of thunderous noise. And interestingly, that points straight towards that Indonesian area where all those volcanoes are.
For the Chinese to have bothered to record such a sound, it must have been an exceptional one-off event. But could the sound of a volcanic eruption have travelled the 3,000 miles from Indonesia to China? To help locate the volcano, Keys asked experts at Los Alamos Laboratory in New Mexico to explain the physics of long-range sound travel.
We know that near the volcano, the sudden explosive eruption provides a shock wave in the near field, and that propagates out, going out to thousands of miles. But as it propagates out, you lose the high frequencies, the shock, very sudden, sharp reports of the volcanoes, and all you're left with are the low frequencies that we measure in what we call infrasound, which is generally below 10 cycles per second. The long-range perception of that sound would be very low rumbling, much like very distant thunder.
The Los Alamos experts had said it was possible. Now, could Keys find any written evidence from Indonesia? Unfortunately, very little writing survives from the area. But once again, he found a fascinating clue. Housed in the royal palace at Solo in central Java is a massive set of manuscript volumes called the Book of Kings, put together in the 1850s but based on ancient sources. It describes an extraordinary event which took place around the middle of the first millennium AD. Today's Javanese royal archivist, Prince Puja, reads from the original text. A mighty thunder, which was answered by a furious shaking of the earth. Pitch darkness, thunder and lightning, and then came forth a furious gale, together with a hard rain. A deadly storm darkening the entire world. In no time there came a great flood. When the water subsided, it could be seen that the island of Java had been split in two, thus creating the island of Sumatra. Had Keys struck gold with the Book of Kings? Geophysicists he consulted said the story accurately described a major volcanic eruption and would have been difficult to invent. But which of the many Indonesian volcanoes was the Book of Kings describing? There was a clue. The only major volcano in that specific area between the islands of Sumatra and Java is the legendary Krakatoa, the world's most notorious volcano, which last erupted in 1883. But could Keys prove Krakatoa was the culprit? An Icelandic volcanologist, Professor Haraldur Sigurdsson, now working in the USA, joined the chase. He had visited the volcano many times and already knew that Krakatoa contained an ancient mystery, an eruption long ago far bigger than anything recorded in modern times.
About 5 years ago, when we were doing research on the 1883 volcanic eruption of Krakatoa, we discovered this deposit of a major eruption, and so we became very interested in this deposit. But at the time, we didn't have the time and resources to study it in detail. So what we really want to do is ideally find charcoal within this layer or charcoal immediately above and immediately below it in order to give us a date of the event.
It was an irresistible temptation. David Keys's ingenuity had led us this far. We had to go on. Channel 4 decided to finance an expedition to Java by Professor Sigurdsson. His goal, to test Keys's theory by dating Krakatoa's major eruption. Krakatoa is part of a group of uninhabited rainforest islands lying west of Java and just south of the equator. It's also the scene of the most famous volcanic eruption of recent times. In 1883, Krakatoa blew itself apart, killing 36,000 people on the mainland. The first stop for Professor Sigurdsson and his team will be the island of Anak Krakatoa, meaning child of Krakatoa. Anak has formed entirely since the eruption of 1883 and grown up into a 1,000-foot-high volcanic island. Each year, Anak becomes ever bigger and ever more dangerous.
Now, actually, when you get up to them, these rocks are the size of houses and 5-6 meters in diameter. And these were ejected by the explosions of Anak, and they travel through the air like a bomb, basically, and they fall to the ground, and when they hit the ground, they create a crater. Well, this is about as big as they come. This one must be 2 meters high. And what do you think, about 4 meters wide?
Yeah, I'd say so.
That's a big bomb.
Yeah, beautiful crust.
Hard to imagine this thing flying through the air and landing here during an explosion, plunking down and creating this crater that it sits in. This one is a good one because you can hide behind it in an explosion and take shelter. Let's hope they don't land like this today. It'll be very dangerous.
Anak Krakatoa is a noisy and quarrelsome child. Only 2 hours after the team pushed off from the island, Anak let rip, hurtling rocks and lava onto the area where we had stood. From the safety of the sea, it was possible to gaze back at one of the greatest firework shows on Earth. This activity is just part of a cycle that's been going on for hundreds of thousands of years. Krakatoa grows up out of the sea. Every little eruption adds more and more rock to the island. Eventually, it gets so large, it blows itself apart. This time, Anak continued its barrage throughout the night, on into the heat and dust of the next tropical morning. But Sigurdsson's task is to journey back in time, hundreds of years back, long before Anak Krakatoa was born. For decades, scientists have thought that Krakatoa contains a centuries-old secret. Illustrations from a 1920s book show a possible pattern. First, there was ancient Krakatoa, which exploded, possibly around 535, leaving islands behind which eventually, with occasional minor eruptions, grew back to the Krakatoa of 1883. This in turn blew up, leaving the Krakatoa Islands of today. Sigurdsson's last survey of the islands seems to confirm this. 5 years ago, he charted the ocean floor using sonar. The charts show the outlines of a caldera, the term for a giant crater left after a massive volcanic explosion.
There's a structure out here in the ocean, a circular structure, which is much larger in diameter, and it is possible that this buried feature, circular feature that we see here to the north and the east, may in fact be a gigantic ancient caldera of Krakatoa. Well, we must be right on the edge here.
So can Sigurdsson find any hard evidence to date this eruption of ancient Krakatoa? Such evidence is only contained in charcoal, which is formed when hot lava instantly carbonizes trees. The charcoal can then be carbon dated in a laboratory. To get an exact date, Sigurdsson must find charcoal from the major eruption layer, which is on the islands around Anak Krakatoa.
Wow, it's a vertical drop.
Failing that, he could also narrow the margin if he finds charcoal in the layers above and below. Looking for charcoal is like looking for a needle in a haystack, and a lot more dangerous.
I'm right in the middle of this major pyroclastic deposit that is formed by a very large eruption of Krakatoa. Now this is very likely to be the deposit that was created by a eruption possibly in the 6th century AD, and this is the one I'd really like to get some charcoal from so we can date this very important event. Now we'd be very lucky to find charcoal, but I'm going to keep digging around here a little bit and see what we got.
The material in the layers of Krakatoa spans hundreds of thousands of years. Even narrowing down the date of the major ancient eruption to within a few thousand years would be a big stride forward.
Often it's extremely difficult to find charcoal. You might think that there would be a lot of burnt wood or carbonized trees here because it's a tropical environment. But many volcanoes are barren because there's so much activity that the vegetation and the forest doesn't really get established. We've had a lot of problem with finding charcoal in this particular deposit, but we must keep in mind that there are only small pieces of the island sticking up above sea level, so we have a very small area to prospect.
During the fortnight he was in Krakatoa, Professor Sigurdsson was only able to find 10 charcoal samples. He was unable to find a charcoal sample big enough to date from the major eruption layer. However, he was able to find good samples for the layer immediately above it and a layer a few levels below it. It will now be possible to see whether 535 falls between those dates. If it does not, David Keys's theory will fall. Six weeks later, the carbon dating analysis is completed. Professor Sigurdsson faxes the results and an accompanying report to David Keys.
Yeah.
So what's his assessment of it?
That's just really good news.
The results showed that the layer immediately above the major eruption is dated as 1215 AD. A layer several layers below it is dated as 6600 BC.
Well, if we look at this in detail over here, then we have this picture. We have 1215 AD right on top here in this deposit. Then we have the major eruption deposit right underneath it. And then we have about 5 layers. And then down here we have the charcoal, and we dated as 6600 BC. So in here we have quite a period of activity and development of the volcano, possibly several thousand years. And that leads us to think that the event is much closer to 1215 AD as opposed to 6600. That span still covers the 535 AD event, so it doesn't rule it out at all. In fact, I think as a result of this, we are focusing more and more in on that time frame.
He thinks that the lead period, the lead option, if you like, for when the major eruption that we're talking about took place was the first millennium AD. So although technically it can be anything between 6600 BC and 1300 AD, all the other pieces of evidence that he's got suggest that it's actually, we can narrow that down to the period, let's say, 0 to 1000. Now, 535 is marvelously right in the middle of that window. So I think that it's looking good.
David Keys's 5 years of detective work suggest that there is overwhelming evidence of a massive volcanic eruption around 535 AD in the tropics. Krakatoa is now the most likely culprit. The volcano that did go up in 535 AD would have produced a dust cloud that enveloped the world. It would have been one of the most dangerous spectacles ever seen. A 30-mile-high column of ash and dust brought global climatic catastrophe. Darkness, drought, frost and famine, and ultimately chaos and war. It was a natural catastrophe that would change the course of human history.